welcome to In 5 Minutes. The agenda of this clip is to understand the concept of carry look-ahead adder. We have discussed the concept of bitwise group generate and propagate signal in the previous clips. Also, we have discussed the concept of group-wise generate and propagate. Let's see how this helps us in predicting the carry for a carry look-ahead adder. The name carry look ahead adder itself says that we can predict the carry or we can look ahead for the carry irrespective of my carry to that stage or irrespective of my carry to the entire block. We'll understand these terms as we go ahead in this clip. Let's get started first with the basics, which we have already done. We will recap all of that, and from there on we'll understand the concept of CLA. Okay. So I've drawn quite a few things on the screen. Let's take each of them one by one and let's start filling up. So here I am showing a 1-bit adder which has inputs A and B and has the C in coming in. And I've assumed that my A is 1 and my B is 1. If my A is 1 and my B is 1, we all know that my generate signal will be equal to 1 because generate is high when A and B both are high. When generate is high, I don't need to wait for my C in. My C out is high, and at this point of time, my propagate would be equal to 0 because propagate is high if my A is high, or in simple words, my propagate is high if my A and B are alternating. So if there would have been a case where A is not equal to B, means one of them would be a 1 and another one would be a 0, then my propagate would have been high. And in that case, my C out would be equal to C in. So this is nothing but 1 bit which you have already seen in the previous clips. Let's go ahead and see a 2-bit block where my input is C0. This is my first block, this is my second block. So this is going to be my MSB, this is going to be my LSB. Inputs and carries are as mentioned. Let's see a few cases. The first case says that A is high, A2 is high and B2 is high. That clearly says that G2, because both A and B are high, so G2 is going to be 1. If G2 is 1, my C2 is equal to 1 and I don't have to wait for C1. However, let's see another case. If A2 and B2 are not same, that means this both are not having the same polarity or the same value. That means they are complementary to each other. That clearly says that they are alternating. When they are alternating and they are not equal to 1, G2 will be equal to 0. Because they are alternating, P2 will be equal to 1 because P is high when A and B alternate. So bitwise propagate for second would be 1. And because the propagate is 1, C2 would be equal to C1 because we know that when propagate is equal to high, C out is equal to C in. Here C out is C2 and C in is C1. So C2 equal to C1. At the same time, so that means this guy is propagating. The first case which we saw was this guy was generating and my output was equal to 1. The second case which we are looking at right now is this guy is propagating, and the input conditions also says that A1 and B1 both are 1. When both of them are 1, that means my G is going to be 1 because the bitwise G is high when A and B both are high, and because G1 is 1, C1 is going to be equal to 1. Because it does not need to depend on C0 then. My C1 is 1 and C2 is equal to C1, so my C2 is also equal to 1. There are two cases which we saw here. One was my MSB generating and other one was my MSB propagating and my LSB generating. This or this, in either case my C out is going to be high. So we just saw that G2 is to 1 or group generate for 2 blocks is nothing but if G2 is high, that is second block has a generate high, or if second block has a propagate high and the first block has its generate high, then G2 is to 1 is high. That clearly says that my C2 is equal to 1. Now let's take another case as well. This is for the propagate. Suppose my A and B are having opposite polarity, A2, B2, and so is the case with A1, B1. Because they have opposite polarity, we can easily say that individual A and B both alternate, A2 and B2. That means propagate is going to be high. A1, B1 also alternate, so propagate is going to be high. Both are not 1, so generates are zeros. So this guy is propagating and this guy is propagating. That clearly says that my C2 will be equal to C in. So the group propagate signal says that my MSB has to propagate and my LSB has to propagate. In that case, I can predict that my C out has to be equal to C in. So let's just write that P2 is to 1 is nothing but P2 and P1. So second bit propagating and first bit propagating. Cool. Now I think you've got the knack of it. Let's quickly do it for the 3-bit and then let's jump into carry look ahead adder. So here I have drawn a 3-bit. Let's quickly do it. A3 and B3 both high. That means the generate is going to be high. And if generate is high, we know that C3 is high irrespective of what's present here or here or here. So that's case 1 done. Case 2, A3 and B3 are alternating. If that's the case, that means my G3 is 0 because they both are not 1. Because they both are alternating, that means my propagate signal is high. So this guy is propagating. At the same time, I'm seeing that A2 and B2 both are high. So if that's the case, my C2 would be 1 irrespective of my C1 again. And here we know that C2 is 1, but we saw that when propagate 3 was high, that means C3 was equal to C2. In simple words, my C3 is also equal to 1 here. So we saw 2 cases. Let's see the final case. The first case was S like 2 bits, MSB generating or MSB propagating and the middle bit generating. Let's see the third case quickly. Here it says that A3 and B3 both are not same and A2 and B2 are also not same. If that's the case, we know that this generates will be 0 because they are both alternating, so the respective propagates would be high. Because P3 is high, that shows that C3 is equal to C2, C out is equal to C in. Propagate is high, so C3 is the C out and C2 is the C in. C2 equal to C1. But now we see that A1 and B1 both are high. If that's the case, generate 1 is high. And because generate 1 is high, they are mutually exclusive. Propagate has to be 0. Or because A1 and B1 both are 1 and they are not alternating, propagate is equal to 0. And we don't need to wait for C0. We can straight away say that my C1 is equal to 1. That means my C2 is equal to 1. That means my C3 is equal to 1. In nutshell, what we just saw right now was my C3 is equal to 1 if my group generate is high, and group generate is high is nothing but G3 is to 1, which says that if my third block is generating or my third block is propagating, this is propagating and this guy is generating, second block, or my third and second block both are propagating whereas my first block is generating. In this case, my G3 is to 1 is going to be equal to 1 and that will make my C3 equal to 1 without being dependent on the input carry. Cool. Let's do the last case. If A3 and B3, A2 and B2, A1 and B1, all these are ANDs, okay? If all of them are not same, we can easily say that my G3, G2, G1 all are zeros. However, because all of them are alternating, all my respective propagate signal P3 is going to be 1, P2 is going to be 1, P1 is going to be 1, all are going to be 1, which clearly says that my C3 will be equal to C0 because this guy is propagating, this guy is propagating and this guy is propagating. That is nothing but P3 propagating, P2 propagating and P1 propagating. So this gives us group generate and group propagate for 2 bits and 3 bits. Now we can generally write it for 4 bits because we are going to enter into carry look ahead adder now. So G4 is to 1 is if the 4th bit is generating, or if the 4th bit is propagating and the 3rd bit is generating, or 4th and 3rd both are propagating and 2nd bit is generating, or 4th, 3rd, 2nd all are propagating and the 1st bit is generating. If this is satisfied, then my G4 is to 1 is going to be 1 and that clearly shows that my C4 would be 1 and I don't have to depend on anything else. P4 is to 1 says that my C4 would be equal to my C0 if all the 4 blocks are propagating, which is nothing but P4, P3, P2 and P1. If all of them are propagating, that clearly shows that my group propagate signal is high, and if my group propagate signal is high, my C4 would be equal to C0. So I think let's translate this group 4 is to 1 generate and propagate into the gate level diagram. What does this tell us? It tells us that if my group generate G4 is to 1 is equal to 1, that means my C4 will be equal to 1. Is that clear? So if this is equal to 1, my C4 is to 1 is equal to 1. Or it says that if P4 is to 1 is equal to 1, then my C4 is equal to Cin. So very simple. Let's quickly draw this. It's nothing but our OR AND gates only. Let's see if that makes sense to you. So this is P4 is to 1. If P4 is to 1 is equal to 1, you want your output to be equal to Cin. So if Cin is equal to 0, the output would be 0. It's an AND gate. If Cin is equal to 1, your output is going to be equal to 1. And if G4 is to 1 is 1, then your C4 will be equal to 1. So if G4 is to 1 is equal to 1, your C4 is equal to 1, or your C4 would be nothing but, depending on the value of P4 is to 1, it will depend on Cin. So this is nothing but a simple gate level diagram which we are going to do with equations also for the carry look ahead adder. I am repeating this. If G4 is to 1 is equal to 1, my C4 is equal to 1, or G4 is to 1 is not equal to 1, can be that P4 is to 1 is equal to 1. And if P4 is to 1 is equal to 1, then my C4 is equal to, yes, that's correct, is equal to Cin. What will happen if G4 is to 1 is also not equal to 1 and P4 is to 1 is also not equal to 1? You remember we studied 3 signals G, P, K, and they were all mutually exclusive. So if this both are not 1, that means group kill would be equal to 1, and that means my C4 should be equal to 0, which you can easily get from this gate level representation also. If this is 0 and this is 0, then your output C4 is going to be 0, and hence we get an adder where we can predict the carry by just looking at group generate and group propagate. Now let's understand how do we get the same carry look ahead principle using the equations of Cout. Let's quickly do that. See, Cout is equal to AB plus BC plus AC, which is nothing but, if I Cout equal to AB plus C in common into A plus B. Now we know that generate is nothing but A and B, and we also know that propagate is equal to A XOR B. Now just look here and see what I'm going to do here. That means here we can say that in general language, this is nothing but Ci equal to AI Bi plus previous stage carry is nothing but Ci minus 1 into Ai plus Bi. Fair enough? Yes, great. Now see what I'm doing. Ci, Ai and Bi is nothing but Gi, so I'm just putting that as it is, plus Ai plus Bi, I'm putting it as Pi and Ci minus 1. Now a lot of people have their eyebrows raised because this is an OR gate and I have called it as a propagate signal, whereas we know that the propagate signal is nothing but A XOR B. Let's understand what I have just done here in the equation. Let's quickly understand that. Let's write the truth table. What I just derived here was Ci is equal to Gi plus Pi Ci minus 1. Let's write the truth table for OR and XOR gate real quick. 0 0 0 1 1 0 1 1. This is 0 1 1 1 0 1 1 0. Now if you look at it properly, you will come to know that XOR and OR differs only in the last case in the truth table, and that's the case when my A is 1 and my B is 1. And if that's the case, A is 1 and B is 1, that means my G is always going to be 1. So my Cout will be 1 irrespective of this term, and hence it is not wrong to substitute A plus B as P, though P is A XOR B, because I will get the same functionality, and that's the reason I have put A plus B is equal to P. Now let's quickly write all the equations here. So we know that Ci is equal to Gi plus Pi Ci minus 1. Let's substitute I is equal to 1. That is C1 is equal to G1 plus P1 C0. Let's call this equation 1. C2 similarly is nothing but G2 plus P2 into C1. Let's substitute C1 from equation 1 here, which is nothing but G2 plus P2 G1 plus P2 P1 C0. This is equation number 2. If you see now, C2 does not depend on C1, C2 just depends on C0. We'll see this further. Let's see C3 also real quick. C3 is nothing but G3 plus P3 C2. Let's substitute the value of C2 here. So that is nothing but G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 C0. So this is nothing but equation 3. Again, if you see, C3 just depends on C0. It does not depend on intermediate carries, which was the problem with ripple carry adder. So we can just predict our final carry just by looking at C in. This is the fun. Now let's finally do it for C4, and then we'll come to a very interesting reduction. So C4 here, let's do it here, is equal to G4 plus P4 C3. Let's substitute C3 here, is equal to G4 plus P4 G3 plus P4 P3 G2 plus P4 P3 P2 G1 plus P4 P3 P2 P1 and C0. Cool. So this is my equation number 4. Now what do we know? What is G4:1? Look at equation 4 and look at G4:1. Do you think there is any similarity? Yes. If you look till here, G4, P4, G3, P4, P3, G2, P4, P3, P2, G1. So this is nothing but terms till here are nothing but G4:1. Then a plus sign. Then can you see P4, P3, P2, P1 is nothing but P4:1. That is nothing but P4:1 and C0. And this is nothing but my C4. Exactly the same thing I have drawn here. So my C4 is equal to 1 if my G4:1 is 1, OR means an OR gate, and an AND gate which has input P4:1 and C0. In this case, Cin is equal to C0. This is the concept of carry lookahead adder. Now, if I tell you how to implement a 16-bit carry lookahead adder, it becomes a very simple block diagram from here on. Let's quickly do that. This is how it's going to look, guys. So what we'll have is, we are trying to do a 16-bit CLA. What we'll have is 4 blocks. I'll tell you what is there in each of these 4 blocks. So internally here we will have G4:1 and P4:1, which will be a combination of AND on OR gates. So G4:1 and P4:1, correct? This will be G8:5. Again the same thing, only the names are changing. P8:5 because it's 5th bit to 8th bit. The equations will remain the same for 4 bits, only the terminologies are changing. Here it will be G12:9, P12:9. They are blocks. Internally they will be implementing this and this in these blocks. And here we would have P16:13 and G16:13. Very straightforward. We are implementing 16-bit. So if generate G4:1 is high, here we'll have the combination of our AND and OR gates. Very, very simple. So this is my AND gate, this is my OR gate, AND gate, OR gate, AND gate, and an OR gate. So let's see quickly. This will be my C4, correct? This will be my C8, this will be my C12, and this will be my C16. And we know the connections are same as here. So if G4:1 is 1, my C4:1 is high. If P4:1 is 1, then this is going to be my C0 or Cin. That will come as the input, and this will go as a second input to the OR gate. Correct? Is everyone clear about that? Let's do it for this as well. So if G8:5 is high, my C8 is 1. Or if propagate is high, then it will take its other input as C4, which is the input to this stage, and this will go to the OR gate. So this is C8. Similarly, we can do it for the other gates as well. Remember, this is nothing but my OR gate. Don't get confused. So I'll be taking the generate here. The propagate will go here, and this will come here. As we have seen, it's very straightforward now. Propagate will come here, this will come here, and this is nothing but this. So This gives me a 16-bit adder CLA where you can predict the output just by looking at your Cin and with the help of group generate and group propagate signal. So suppose if you want to find the sum of this 16-bit CLA, we know that sum is nothing but A XOR B XOR Cin, where A XOR B is nothing but P, which is XORed with Cin. So for each corresponding bit, you can have your corresponding P and its respective Cin, or there is another logic also which we can use, but currently sum is not in the critical path, or sum is not very important to us. We are more concerned with C out, and that's the reason this is enough for you to know a 16-bit CLA, how carry is made faster. With that, I hope you have followed this. Stay tuned for further clips, and thank you very much.